Hello everyone, let's have a look at the new blade development feature in Centrix. So I've loaded up a BC219 fan here. Now this fan has a conical shroud and the blade has a straight leading edge. So let's just have a look at this new feature. So here's the blade development. So this is to cut a flat plate before it's pressed into the shape. Actually, we'll have a look at the shape first in the impeller assembly. So let's draw that. So we can see the blade here. So it's got a curved section and two straight portions. It's quite a thick blade for the diameter of the impeller. And that is because we need a low blade stress. We can see that non-destructive testing is recommended there. So now that we've had a look at the impeller assembly, let's have a look at the blade development. So now this is the new feature. So in the past, we would have jumped straight to use the blade development block. So let's just have a look at that first. So that is the standard development. Which is generally would be the top surface of the blade. So when that blade is formed, shaped, and joins the shroud, we don't get a nice joint if we just use the top profile. So we've got quite a bit of weld to fill in here if that's what we do. So let's have a look at the automatic blade development. So the automatic development is going to show three surfaces that could be used as the profile for cutting the flat plate. So the top, middle and bottom surfaces. And now you can also see that we've got a grayed out section here for the speed ring. So let's draw that. So we've got this note that the development process was unable to trim the construction line back to the shroud. So let's just have a look and see what that means. So here are our three ways, if you like, to cut this blade. We could use the bottom surface, in which case we'd have to grind the top back to get the blade to fit up against the shroud. We've got a middle surface, which will require a bit of grinding and a bit of welding, and the top, which requires no grinding but quite a bit of welding. So we've got a difference between the top and the bottom here of 9 millimeters. So that needs quite a bit of grinding in this area if we're going to use the bottom surface. At the top edge, we've only got a difference of 2 millimeters between the top and the bottom, which could easily be welded if we just use the top. So having seen that, oh, by the way, this little square edge here is what that message was about. So this is the part of blade that hangs over the shroud. So let's just go back and have a look at that. So this is the blade joining the shroud, but this edge here, although we've got a radius on there, the development shows it as a square edge. So if we just draw a circle to this edge and we project that across to where it should join the shroud, we can see that it actually misses the shroud, and hence we've got this square cut where the bottom of the blade misses the inside of the shroud. So let's have a look again at that. So that's that message, and that's how it looks. So having done that, we might decide that, okay, let's just draw the middle surface. That's what we'll cut, and we'll do a bit of grinding. So we can actually print out both of these drawings. We could print that one and say, okay, well, grind this area here. So we could do a dimension, say from here to here and say, okay, this area needs grinding to cut back. And then we could just do the surface for the profile that we want cutting to send to the plasma or laser cutter. So let's just go back to the options, or to the blade design, I should say, and let's have a look at speed rings to lower the stress, which means we could perhaps use then a thinner blade, 3mm say, which is okay. And let's just draw that. So they're the two speed rings. Let's just see if they can be made a bit thinner. The stress is very low. The shroud is 3mm, so we might want to say we can use 3mm for the speed rings. And so let's draw that. That looks okay. Now let's draw the blade development. And now we've got this option to show the maximum slot size for inner and outer speed rings. So let's just draw that. So we can see now that because we made the blade thinner, we've lost that square cut on the end, so that the blade now joins the shroud at this leading edge. And now we've got a magenta slot size here. So we can see the slot size for using the bottom, the middle and the top edges. So that, again, we had to do some grinding if we just use the top to get the speed ring in. Or we could cut this maximum slot and just fill it with weld. And the same with the outer speed ring. Now the thing here is, if we are developing the middle surface and we want to show this maximum slot size, we can show it here like so. And then all we have to do, if we're sending this to a laser cutter or plasma cutter, we can delete this yellow slot line from the top and bottom slots for the speed ring. And again, if we compare that to the, let's call it the old method, then it is a much less featured. And this is just shows a straight line. Whereas if we use the automatic, we can see that this is not a straight line. It is actually an arc. If I turn on the grips using Ctrl-G, we can see that it's an arc and not, I might draw a white line from there to there. So it's not much of an arc, but it is an arc. And these profiles are actually polylines because they're so detailed. So you may wish to manually draw arcs and straight lines on these polylines to make them easier to process in the nesting software. Okay.